Hello, everyone, dear authors and dear invited guests. Welcome you all to the technical session 3B. On behalf of Global Knowledge Research Foundation, it is my great pleasure to welcome you all to the 7th International Congress on Information and Communication Technology through Zoom. Further, as we all are aware that we have been facing new normal situations while overcoming the pandemic, hence the conference has been shifted to a hybrid mode. We are very thankful to everyone present on this platform to go along with us digitally for the conference in these unpredictable circumstances of post COVID-19 and making this conference more productive. Also, I wish everyone and their families a protected time. And I hope you all will enjoy this knowledgeable and interactive digital session. Also, there is a special note for all the presenters that you will be given 10 to 12 minutes for your presentation and further 3 minutes for your question and answers. On 10 minutes, I will raise a gentle reminder. And I request while the presentation is going on, other participants kindly be noted. There is another one request for the participants that all stay connected with us till end of the session. Just before we get start our session, I would like to introduce you all to our session chair. Hello, am I audible?
Yep.
Yeah, so I would like to introduce you all to our session chair, Mr. Ezekiel Uoki. I hope I pronounce a right name.
Okay, I'm Dr. Okike.
Yeah. So, sir, the BSc, the Master of Information Science and PhD from the University of Ibadan, Nigeria in 1992, 1995, and 2007, respectively. He is currently a senior lecturer and the cluster chair of Information System Cluster, Department of Computer Science, University of Botswana. He is a senior member of IEEE and a member of SEM2. His research interests are in software quality, models and architectures, software measurements, information systems, software engineering, machine learning, information security, cyber security, and e-system. So I warmly welcome you, sir, in these interactive and international conference and our digital session. So
thank you.
It's up to you, sir. Yes, sir.
Yeah, we are welcome to the conference this time. This is session 3B. Do we have the very first presenter? Gule Kambalohu?
Yes, hello.
Okay. Can you go ahead and present your paper on computational modeling of the role of leadership style for its context-sensitive control over multi-level organizational learning?
Wow. I'm sharing my screen.
Okay.
Can you see?
Yeah, we can see your screen. You can see your slides.
Okay. I am Gülay Cambaloğlu, and I will present our paper, Computational Modeling of the Role of Leadership Style for its Context-Sensitive Control over Multi-Level Organizational Learning with Jan Treur and Anya Viviora.
Okay.
Today, I'll talk about mental models as relational structures in your mind first, and then I'll explain multi-level organizational learning with its levels. And then I'll talk about role of leaders in multi-level learning. I will describe our example scenario. And finally, I will show our simulation results to you. Mental models. We all have mental models to learn things. We observe and sometimes try to imitate others to learn new things since we are born. We try, we fail, we succeed. We use our mental models when we communicate with each other and while we try to understand things. The internal creation, adaptation, and improvement process of our mental models provide us to comprehend concepts and their relationships between them and also with us. In other words, learning takes place with in-person mental models in our minds. Overall cognitive architecture of mental models have three main layers: usage, adaptation, and control of adaptation. It's clear that we use mental models to learn the real world as abstract representations. This lifelong process of using mental models takes place depending on some factors like people or things we interact with, or our current mental situation, or the place that we are in, and so on. However, under any circumstances, we continue to use our mental models until we die. But of course, our mental models do not stay the same as they were. They adapt through learning and forgetting by time. Many different ways of learning develop the mental models we have by increasing the strength of the connections between the concepts in our brain and their real life counterparts. And understandably, forgetting weakens these connections. There are again many factors affecting the adaptation process of a mental model, and we will focus on one of them in this presentation, the role of leadership. The existence of a leader and the way he or she applies his or her leadership style closely affect the learning process. We will talk about this later in detail, but it's important to say that leaders have the power to influence the aggregation of mental models of team members as much as adaptation of them. At the top, a third layer for control of adaptation exists. Adaptation speed and persistence can change person to person and from team to team and organization to organization. These two basic but important factors control the adaptation process. For the self-modeling networks, we have representations of these layers as like in the right-hand side. For the use of mental model, we have base level. For the adaptation of a mental model, we have first order self-model level. And for the control of adaptation, we have second order self-model level. Multi-level organizational learning have feed-forward and feedback mechanisms, as you can see in the picture here. Multi-level organizational learning have these 6 different levels. We have individual level in the beginning and in the end, but these are not the same. I will explain in a minute. We have individual level in the beginning. It's the learning within and between individuals, the improvement of individual mental models. We can see the circular arrow here representing this first state. And then we have feed-forward learning from individual to team level and from team level to organization level. These are the feed-forward learnings. And we have feedback learning from organization to teams and from teams to individuals. And in the end, we have individual level again. It's the improvements of individual mental models by feedback learning from organization or from their teams. Role of leaders in multi-level learning. Leaders have very big impacts in multi-level organizational learning. They are also called social architects of organizational learning by some research. They have the ability of facilitating learning and also inhibiting the learning. Because they are like intermediary persons between the different parts of organization, they access to different departments, different peoples from different departments. That's why they can facilitate same level learning flows, like individual to individual or team to team. And also they can facilitate feed-forward learning flows, like from individual to team or team to organization. We have an example scenario. Variables identified in our example scenario are learning from past experiences. We will have Tom as an experienced project manager, and he will learn from his previous experience. We have role of leaders to effectively transfer learning and institutionalize learnings. We have different type of leaders, and we have a resistance to learn from a novice. And one of our leaders will resist to Tom. Alpha is our hierarchical organization in our scenario. In this scenario, shortly, I can explain it. Tom first uses his previous experience to adopt a shared mental model here. He decides on second team. He experienced two different teams and decides on second team to adopt its mental model because it's better. And then he shares the shared mental model with the third team, and the feed-forward learning takes place here. These are the conceptual mechanisms extracted from our textual scenario, and we found the computational mechanisms reflecting the conceptual mechanisms. Then Tom shares his idea with manager D, but it's not approved. The manager D's leadership styles doesn't approve the proposal of Tom. Thus, no feed-forward learning happens here from team to organization. But after months, Tom proposed his idea again to a different leader, manager E, and it is accepted. Then the organization adopts this shared mental model, including Tom's proposed idea, and feed-forward learning happens here. This is the difference between internal learning by internal simulation and learning by observation. I can skip this part because we don't have too much time. This is the abstract view of the model. In base level, we have the skeleton of the overall model, actually. Shared mental model states starts with this abbreviation, and IMM is for the individual mental model states. We have shared mental model states for teams, team 1, team 2, and team 3, and also organization. And individual mental model states for A represents Tom, B and C represents the teammates of Tom. In the first order self-model level, we have double states to control and activate the base level states, adaptation of this base level, the network actually. And in the second order self-model level, we have the states for higher order double state and H state for control of adaptation. H state is the control of speed of adaptation. This is the simulation results only for team 1 and team 2, the previous experience of Tom. Tom saw that the last task of team 1 is below than the last state of team 2. That's why he decided on team 2. The green one is for team 2, the red one is for team 1. And this is our overall simulation results. In the beginning, here in this first part, the first and second teams learn their shared mental models. The team formations occurs here. Then here, Tom decides to adapt the shared mental model of the second team because of the better results and adapts it. And then Tom shares his mental model coming from the shared mental model of the second team with his other team members, B and C, and in his new team, the third team, here between 300 and 400. And then formed shared mental model is proposed to manager D. As I said,
just try to round up.
Okay. Should I conclude?
Yes.
But manager D doesn't approve it yet here, but here in the last part of it, manager E, the other manager, approves it, and the institutionalization occurs here by the feed-forward learning. Thanks for listening. This is all.
Okay. Any questions for the presenter? Okay, no questions. I would like to know if the models, the mechanism model, as well as the abstract view model, are they yours? Or you borrowed them from the work of some other person?
You mean this one, right? Can I?
Yeah, the mechanism model and then the abstract view model. Well,
Yes.
all the models you use, are they yours or they are from other work?
Yes, they are ours.
They are yours.
Uh-huh.
Okay.
We developed them.
You developed the models. What did you use to do the analysis?
For the analysis, for simulation, you mean? We used MATLAB.
You use MATLAB.
Yeah.
What is the difference between what you are doing and learning analytics? Is there any relationship? You have not heard about learning analytics?
No, I don't.
Okay, you need to check in order to find if there is any relationship between multi-level learning, how it relates to ICT, and of course, learning analytics, LA.
Okay.
Any other questions? Okay, thank you for the presentation. That was nice.
Thank you.
Thank you.
All right.
Thank you so much, sir, and dear presenter, for your excellent presentation. And now I would like to invite our next presenter. Let me show you. So our next presentation will be driven by Mr. Christoph Uran, and his paper title is Annotated Automated Network Evaluation and Test Environment. So yes, you may please start your presentation. All the best.
Yes, I will just share my screen. Thank you very much. Can you hear me?
Yeah.
Okay. Yes, we do.
Okay. Can you also see my screen?
It's off now.
It's
Bring it back.
Just a moment. So now you should be able to see my presentation.
Yes, it
okay,
is.
Perfect.
It's here.
Yes, thank you very much. I'm very pleased to be able to present our paper with the title of ANETTE, which is an automated network evaluation and test environment. My name is Christoph Uran. I will present this paper on behalf of my colleagues, also Valentin Egger, Kurt Horvath, and Helmut Wöllig, who is also the leader of our research group Roadmap 5G here in Klagenfurt. Okay, so just to give you a very, very quick outlook about the agenda, I'm going to give you first a small introduction about what exactly we are doing here. Then I'm going to tell you something about the problem at hand we have in our research network. I'm going to show you the setup of our system, which we propose and which we have already implemented. Then I'm going to show you the reports that are being generated there, and then I'm going to round up with the results and the discussion and the conclusion. Good. So like I announced, first I will give you a small introduction, the small background. Nowadays, we are, of course, surrounded by computer networks, may it be cabled networks or Wi-Fi, LTE networks, or nowadays even the 5G networks. And many parts of this infrastructure can also be considered to be a critical infrastructure. So it would be very, very bad if there would be some outages or if there would be reduced performance. That would, of course, have very, very bad effects. So therefore, it is quite important to have constant measurements and tests of these systems. With constant measurements and tests, I mean, they should also be of course, taken into account. They should be stored inside the database, and then they should also be verified with the help of KPIs, of key performance indicators, so that we can have a long and short-term comparison of how the network was performing before, then we did maybe some changes, and how it's performing afterwards. So, of course, this is a very important part, especially in a research network such as this 5G Playground Carinthia that we are operating together with some partners. And this research network consists of many different parts, obviously, but just to give you a quick idea of the components that we have there. First of all, we have got a 5G and of course also 4G. So it's a non-standalone campus network. So it's a non-standalone 5G network, which consists of 4G base stations and 5G base stations. We even have got our own mobile core, so our own mobile phone core, which was provided by the company Hyperblox. And this core is inside this network. We can do basically anything. So we can do stuff that is not possible to do in a public mobile communication network. So it's really a research network where the researchers say they need these parameters. They need some own SIM cards to test something, and then we go ahead, give them the SIM cards, and configure everything. But the whole idea of the system is that this also runs inside our own private cloud. So it's not really a private cloud. The cloud is provided by a company called Exoscale, and Exoscale is, I would say, a competitor of AWS, for example. And normally they've got data centers all over Europe and also some outside of Europe. But what makes them really special is we also have got our own edge data center here in Klagenfurt at the playground. So we can provide very, very low latency for the communication needs that we have. And of course, the 5G network needs very, very low latency. So this is the Exoscale cloud. And then, of course, we also have our enterprise network, which is basically a normal network consisting of switches and firewalls and everything that you need from a normal network. Inside this research network, we have got 5 different use cases right now. And they are doing their research in different areas. So the research areas are connected drones, so drones that are connected via 5G, robotics components that are connected via 5G. Then, of course, we have got smart cities, virtual realities, and also fog and edge computing. These are the use cases that we provide here. Okay, and the problem at hand here is, of course, these use cases, they want to rely on the performance of the network. So the network should always be at its best performance. But how can we verify that this network is actually working as it should? And you can see here the network we are working with here is a very complex network and a very heterogeneous network. So it consists of different components. And now, of course, a standardized test of these components can be very, very difficult because it's very distributed. And for that, we created our own solution. Of course, there are solutions on the market that maybe partly already provide that, but they don't have standardized interfaces most of the time, and they also cannot create automatic reports and stuff like that. So that is why we decided to create our own distributed solution. And this distributed solution that I'm talking about is Annette. And this Annette system basically consists of 4 main components. These 4 components are the manager, the database, the reporter, and the worker. So I'm just going to give you a quick outline about how this system works. Can you also see my mouse when I move it around here?
Yes, we do.
Okay, perfect. So let's start with the manager here. This is basically our main, our centralized component. And the manager always reads for measurement specification inside the database. And when the time comes, according to the schedule, to create a measurement or to execute a measurement, it instructs the individual instances of the workers which are doing the measurements. And these measurements can be iPerf measurements, they can be ping measurements, so to test the latency, they can be all kinds of measurements. And when the workers have finished with their measurements, the manager gets the results and stores them inside the database. So that is for that part. But we also have got the Annette reporter, and the reporter is basically a Jupyter notebook with some predefined templates for the analysis. And this reporter reads the database and checks what kind of performance we got at certain tests. And this can, of course, be done by the operator that is symbolized by this small man here. Okay, this is the basic. These are the basic components of the system. And now, if we generate these tests, what I have to mention before is that the interfaces that we have here in between, they are standardized interface. So here, for example, we've got the RESTful web interface, which of course can be utilized by any other component. So it's not vendor specific or anything like that, but it's very open and very open for other collaborations. Okay, and the reports that we are creating here are, this is one example for a report. This is an overview report. And what we can see here is, for example, which 2 clients did the test. So between which clients it was tested, when it was tested, what the type of test was. Like I said before, it can be either iPerf, so a normal TCP or UDP test, or it can be a ping test. how long the test was executed, what the options were. So there can be either TCP or UDP or ping, like I said before, and also just a really quick summary of what this of how this test performed. So this is a very, very, very nice view for the administrator to see some kind of historic comparison, or to see some kind of comparison about how the network is performing right now. And on the next
summarize,
slide,
please.
yeah, on the next slide, we can see the detailed reports. And you can see here, we've got a very nice plot, and we've got a detailed analysis of the tests. So most of the stuff that is on this slide, I already told you before. Before we had Annette, it was very, very difficult to make it automated and to have a unified system to test everything. With our system, this is much easier. Yeah, and basically with Annette, we can provide an automated, distributed, fully containerized. This is something I didn't tell you before. All the components are containerized. They are Docker containers. Yeah, fully containerized network tests and measurements with full reporting and the full documentation that is needed for that. Okay, thank you very much. I hope I'm on time, and I'm looking forward to your questions.
Yeah, thank you. Any questions for him? Any questions so that we can interact?
Thank you. Sorry for interruption. I will be the moderator for the rest of the session, and we can't find any question on the chat. So you can go ahead, the professor, if you have any question or discussion for him. Thank you again.
Yeah. What about security issues? You didn't touch anything about security?
No, we didn't touch security so far, but it is planned to have at least Nmap port scans inside Annette, so that we can at least check if certain ports are open, which might be vulnerable to security issues. So this is planned for the future. The system is right now still under very active development. So, but this is planned on the roadmap. Yes.
Why did you choose Python?
Because it was.
Why do you think Python is the most appropriate for this experiment?
Because what we did here is we focused very much on containerization, and when we containerize our workload, it is quite, to be honest, it's very convenient to use Python. It's also for the statistical analysis of the measurement data that we have here. It's Python. I would say is a very convenient language to do the analysis of that. Of course, other languages might be more performant. It might be better to use other languages if we focus on performance, but in this case, we didn't do that.
Yeah, an important aspect is that of security. So you think deeply as to how to secure the system and so
concerning
on.
Security,
any other questions?
Concerning security, because you mentioned it, we've got everything containerized inside Docker containers, and we expose only those ports that are actually needed for the measurement.
Okay. Any more questions for him? Good presentation. Can we move on? Thank you.
Thank you very much. Thank you.
Yes, for sure. Thank you again for the presentation and for the feedback. I'm pretty sure that you will consider the notes related to security for future improvements, and all the best again. So now, hi everyone. Sorry, I joined late. I'm Fayuz, and I will be the moderator for this session and for the rest of the conference. So now we are moving forward to another great idea regarding security and privacy receiving access data protocol in vehicle corresponding using a blockchain. It will be presented by Mr. Abdulrahman on behalf of the co-authors. So it's over to you, Mr. Abdulrahman. I will stop sharing from my side, and you can share. Meanwhile, if there is any question, please feel free to post it to the chat or to me directly, and I will share it. It's over to you, Mr. Abdulrahman.
Hello, everyone. Hello. You heard
Hi.
my... You heard me?
I can hear you and see the slides.
Good morning, good afternoon, good evening. Because of your time, I am an assistant professor in Jazan University. My name is Abdulrahman Al-Amir. My paper is, our paper is talking about security and privacy preserving accessing that protocol in vehicular cloud sensing. Um, so I will cover vehicular cloud sensing introduction, security challenges, and the contribution and conclusions. So recently we can see vehicles became more smart with sophisticated sensing devices and a capability of computing and storage. So for this sophisticated tools, vehicle cloud sensing have been introduced to support various of mobile applications. So in which vehicles can cooperate with their sensing data to feed many applications. Um, So, for example, vendors or organization can, for this application, can ask for task, and uh, RCU or cloud can recruit vehicles, interested vehicles, to sensing or to cooperate to perform this task and send their sensing data to the cloud server or to this organization for fitting this application. So, and this why we can use these applications. So, cloud server will store this sensing data in the vehicle cloud, or in will be store this data in the profiles of this vehicles in the vehicle cloud. Vendors, then our organization or applications, our customer will access to vehicles profiles and get their sensing data. However, here we can get the security challenges, security and the privacy challenges. First of all, the first challenges is disclosing application private data. For example, if this organization access to the first vehicle, the vehicle one profile, and if we suppose vehicle one participates in different applications, and the cloud store this sensing data in this vehicle files, and when the organization or application one access to this profile, he can knows the other data, the other application data. This is the first challenges. And second challenges is application also can disclose vehicle's privacy. For example, he can knows the locations when he did the other sensing data, the other application sensing data. This is the most challenges discussed in this paper. So solving this, we propose a blockchain with elliptic curve cryptography to introduce a framework based blockchain with the security and the privacy preserving accessing data protocol. So the proposed blockchain consists of, as we know, the blockchain has a header, a payload, and the backside. In the header, it exists of the block identity and the previous block identity. They should be hashed value, and in the payload they consist of task identity, vehicles, so number identity, and the ciphertext, which is the encrypted value of the sensing data, and the secure keys. And in the back side is consists of the vehicle signature and stamp, timestamp. So the purpose of this paper is to solve the confidentiality, integrity, and the authorizations in accessing to vehicles profiles. So the schemes will be started as vehicles. When the vehicles participate in a task, it will generate this value, task identity, and vehicles certain identities, and will encrypt the sensing data and sign in the sensing data, and will generate a secure key, and then will be sent it to the vehicle cloud server according to Rusile unit. Cloud server will then generate this block and store this information in the block. So the only application who has the secure key, he can access to the data. So he cannot disclose any other application sensing data. So the evaluation, the security analysis achieve confidentiality, integrity, and authorizations with the cryptography proposed and blockchain. We can able to achieve this three security codes. Sorry for this. And the evaluation rate of the blockchain storage, this is the most important. We can see the number of the tasks, the unknown task is, if the number of the task is equal number of participated vehicles, for example, if one vehicles perform one task, the storage will be, it will be will not be that large. However, when the vehicles participate in many tasks, the storage of the blockchain will be increased. Here I try to give a quick main idea of our proposals, and the more details will be in the paper. And thank you, and any questions?
Thank you. Do we have questions for him?
Thank you for the presentation and all the best. No, we don't have any question on the chat. So it's over to you, Professor, if you wanted to share any thought or any question. Thank you.
Yeah, I am just, is this work ongoing, or is completed, or is part of an ongoing project?
Honestly, I'm doing, I'm extending this to journal so far, and then after this we can see if we can make it as a real project.
How did you test the implement? Is it implemented? Not yet.
Yeah, there are some tools for cryptography, some tools for blockchain. So we modify this based on our contributions, and we can test it. There are C++ codes. We can do this, and we can generate information with this.
Yeah, I wanted to know the strength of the test data. That is just why I'm asking.
This will be in the extension paper. In the extension paper, we would do more experiences on the informant, and we will get more result for this.
Okay, so it's an ongoing work.
Yeah.
So to say, because there are so many issues in of privacy that is involved, that needs to be taken into consideration in a work like this. Okay, if there is no other question, please just make sure that if you need to implement it, you look into the directions of more security and privacy issues from available
absolutely.
standards and frameworks, so that you take those things into consideration.
All right. Absolutely.
That's just my comment.
Thank you.
Yeah. Can we move on?
Yeah, sure. We can move on. Unfortunately, I think the next presenters are not there, but I will double check in case that any of them are joining with a different name. So the next one would be Mr. Muhammad. If you are here, just please open your mic with any different name, because I can't see you in the audience. Mr. Muhammad is not here. Mr. Sahah, are you here with any different name? Because I can't find you in the list. Okay.
Hassan, are you there?
No. Abdul Fattah, Mr. Abdul Fattah, are you here? Because again, I tried to look into the names, and unfortunately you are not here. Okay. So looks like we very quickly went to the end of the session. So thank you.
But why are they not here? How are they going to expect their papers published when they have not presented?
I think the management team will take care of this since we have tomorrow, so we might get another chance for the representation for tomorrow. So the management team will chase them and send a follow-up. Maybe it's due to technical reasons. So there is another chance. Hopefully they will join us. So thank you everyone for your time. I know it's a little bit late, but again, it was my pleasure to be part of this session. So I sincerely thank all of you, our authors, for the excellent presentations and contribution in this session. Without you, it would never be part of the success. So it's part of the yeah, I'm sorry, there is an echo. So thank you for being part of this international conference, and I hope that the session was informative enough for those who joined. Also, I would like to make a notice that the digital certification will be sent through email within a couple of days for those who already presented. Further, the papers will be published as they are already forwarded to Springer. It usually took 5 to 6 months, so kindly keep an eye on your email and cooperate with ICICT team to make sure that it's already replied in case that anything is missing. I also thank you, Professor, for your time and for being the chair of this session. You added a lot to the discussion. So thank you again on behalf of myself, the team of ICICT and the Global Knowledge Research Foundation. Thank you for everyone again.
I'm so sorry for interruption. Actually, I think our next presenter, Mohammed Farooq sir, is here. So
he joined.
We should
okay,
continue. Okay. Yeah. So we should continue.
Okay. So I'm really sorry
with his presentation. Yeah.
For this. Okay. So yeah, looks like Mr. Muhammad joined late. So I wanted to welcome him, and hopefully no one left the session. And he will present a paper titled as Automatic Jumper Signal Classification Using Deep Learning and the Spectrum of AI-Enabled CRIOT. It's over to you, Mr. Muhammad. You can share your screen. I stop sharing.
Okay. Mohammed, are you there with us?
Hello, good evening. Can you hear me?
Okay, we can.
Yes, we can hear you.
Okay, let me share my screen. Can you see the screen?
Yes. Could you please go to the second slide? Yeah, okay, we can see it. Go ahead. All the best.
Okay. Should I start? Okay.
Yes, please.
Good evening. Good evening, everyone.
Good evening.
My name is Mohammed Farooq, and the topic of my presentation of the research paper is automatic jumper signal classification using deep learning in the spectrum of artificial intelligence, AI-enabled cognitive video IoT network. The co-authors of these papers are Tariq Jamin, Sanfullah Khanzada, Asma Khan from Kennedy University and King Abdul Aziz University, Japan, and myself from Karachi, Pakistan. The outline of my today's presentation as follows. I will start with the introduction, motivation, objective of the work, paper contribution, followed by the proposed method and the considered scenario for our simulations and results. I will explain the simulations and results and the conclusion, followed by in the end, the future work and the work that we have been doing currently. So let's start with the introduction. Recent advantage and information and communication technology, machine-to-machine technology, and artificial intelligence technology have brought a network which connects the various objects to provide service to the user. And this network is called as the Internet of Things. Internet of Things is a feature technology which connects various objects. IoT has provided facilities including many applications such as healthcare, where we can see many applications, technology, we can perceive many technologies around us, industrial automation, using IoT, autonomous vehicle transportation system. And also IoT has provided the concept of smart cities where every object is connected to the internet. has also provided environmental application as well as the social applications. The IoT network consists of the small devices, which are basically the wireless devices. So the connectivity could be hashing through the wire technology or the wireless. However, the wireless technology is more feasible solution in the IoT network. It is suffering from the spectrum scarcity problem. Because the devices doesn't uses the spectrum efficiently. Therefore, it is envisioned to incorporate intelligent and self-aware capabilities into the devices of the IoT network, thereby giving the concept of cognitive video IoT network. Like other wireless network, this IoT network is vulnerable to the various kind of the meshless attack. This attack could be at the physical layer, at the network layer, and the map layer as well. So therefore, detecting and classifying such kind of attack is really essential to make this single IoT network reliable and feasible for secure transmission. Therefore, in this work, we have considered cognitive IoT network to provide reliable transmission. Cognitive radio idea was given by Joseph Motilla in 1991 to give the concept of intelligence radios. Using radios can learn and reasoning about the environment in which they are being operated. Also, they should exhibit the property that is called as autonomous learning and the self-programming. And according to the Hyperion, CR cognitive radio uses brain-empowered capabilities to use the spectrum efficiently and achieve objectives which are the major in the communication technology. So in essence, we can say that it integrates model-based learning with software radio technology to build, adopted, self-configured radio that is being operated in the environment, and that radio should aware of itself and the surrounding environment. To redefine the self-awareness capability of a system is capability to generate the knowledge about itself and the environment in which it is being operated, to determine the action to be executed based on that knowledge which it is continuously acquiring from the environment. So if we incorporate that data-driven, self-aware functionality into the IoT network devices, they can exhibit the following functionalities. They could autonomously learn generative models. They can detect abnormality, and they can learn the new models if there is abnormality emerged when the transmission is being going on. So clearly, IoT network is a network connected, which connect various objects. So the goal is to make that IoT network self-aware, not only self-aware, but also to detect such kind of the malicious attack, which is basically done by the jammer. So we have seen recently, not recently, but we have witnessed that the machine learning models and the deep learning models have been implemented into the many applications such as IoT, vehicles, city networks, and they provide a very promising results for the classification and for the predictions. The machine learning models, we have to extract some of the features, and those features could be fed into the machine during the training and during the testing. Test the model based on that training what we have done. And in the deep learning models, the model exploit the properties of the engine when dealing with the deep learning models. So clearly, the objective of this work is to build the CRIP network, which is more proactive and attack-free to execute its mission. The devices in the network could be intelligent, aware of what's happening in the network, and also to provide the secure transmission. Also, the main objective was to extract and exploit and analyze the CWT, which is the continuous wavelet transform, and FFT, which is the fast forward transform features from the signal, and train the deep learning models based on those features, and capturing and detecting abnormalities at the physical layer in the network. So the work contribution is the classification of the jammer signal in the spectrum which is a cognitive peculiarity spectrum based on the CWT and FFT features expected from the wave signal transmission or the frequency division multiplexing, and use those features to do deep learning models and classify the signals that we have. So we have considered this network in which we do have mobile users which are continuously sensing the environment, and they are receiving the signals from the base station, and the signals that they have been receiving as the OMT modulator signal. And we also consider the jammer which is present in the network, which try to attack the signals at the physical layer and try to increase the bandwidth or in terms of the power and try to deplete the bandwidth. So we have considered this network. We have considered the system model that is basically ICICT and the Google Land, which are two popular models and have been trained on the millions of the objects, and they perform the classification task based on the features that we fit into these models. So we have obtained CWT features and the FFT features from the OEM team received signal from the concealed environment, and trained on these features, the ICICT and the Google Land. So this is a workflow, the system flow works. So we have received OEM signals, obtained the FFT features and the CWT features. Since the FFT features are in the complex samples, and the CWT are the stereograms basically, which can retain the time and frequency information of the signal, what's happening in the time domain and at the same time in the frequency domain. And we obtain and converted that into the RGB image to work with ICICT and Google Land, because they work well with the AELs. So that's what we converted that. And we divide our data set into the training and test, and train these models ICICT based on the features that we have obtained, and we perform the classification. So we made the three classes. So one is the normal signal spectrum, other is jammer with a high power and jammer with a low power. We didn't consider the jammer with very low power because the signal is below the threshold and it is very difficult to detect and classify with these models. For that, we need to consider some statistical property, or probably need to exploit some more statistical property of the OEM signal to go on with that. So we have obtained these kind of results. So on the right-hand side, we do have F15 based Google Land and ICICT implementation. And this one is the figure B is CWT. So more or less the performance of the Google Land and ICICT based on the feature F15 CWT are in line. And we have also compared with the CNN with the simple CNN model with some layers, convolutional layers, and the cooling layers all the way around. And we have seen that the ICICT and the Google Land have performed against the CNN. So obviously the conclusion is that we can either opt with the FFT features or the CWT features. Given that we have the OEM signal transmission, which is a popular signal transmission technique for 5G, and also welcoming in the 6G transmission, so we can opt for the FFT and the CWT. However, if we go with the FFT features, that is inherited property and receiver of the OEM signal, so we can readily extract the features from FFT, convert that into the RGB images, and then we can train Google Land and ICICT. That was the idea that we have done with us. So the feature work is in a line that we have been exploring the short time frequency transform and other transform, and then we have been training the deep learning models to perform the classification task. Thank you very much. And Krishna.
Yeah. Thank you.
Yeah, thank you for the presentation, and all the best for the rest of the research. We don't have questions again on the chat, so I want to just hand it over to you, Doctor, if you have any idea, any thought about this.
I just wanted to know which kind of tool you used to do the simulation. Do you hear me?
We opted firstly for the MATLAB, and then we have also implemented this in a Python. Yeah, I can hear you. Can you hear me?
Yes.
Okay,
but I asked. Okay, go ahead.
Yeah, we have implemented this model in the MATLAB, and also we have implemented in the Python using Jupyter Notebook.
Okay, you use both MATLAB and Python.
Yeah,
Now Okay. Which aspect of machine learning is it focused? Is it supervised or unsupervised?
It's the supervised, because we have defined the classes, and we do have the three classes: normal signal spectrum, and the signal spectrum with a high channel power and the low channel power. So it's a supervised. And now we have been working on the unsupervised, in which we have been deploying some clustering algorithms to exploit these properties in an automatic fashion or in an unsupervised fashion. So that's going to be in line with the self-awareness capability that we have been talking about.
So the current work is based on the supervised model.
Yes.
Okay. Well, that's fine. That's fine.
Yeah.
We can
thank
move
you,
to the
thank you.
next one. Okay.
Yeah, for sure. Thank you. So I wanted just to do a last check if Mr. Hassan is here.
Yes.
Are you here?
Hassan is there. I think I saw him enter.
Okay. So Mr. Hassan.
Hassan, are you
hi,
there?
can you guys hear me now?
Yes, we can.
Yeah, okay. So yeah, most welcome, Mr. Hassan. It's my pleasure to introduce your research titled as Performance Evaluation of Boost-to-Stream TCRnet on behalf of the co-author. So the floor is yours. We are all listening to your presentation. All the best.
Okay.
Okay, can you allow me access to share a screen?
Yeah,
I think
you can access. I stopped sharing. Yeah, I stopped sharing. Could you please try now?
Yes, can you see
Okay,
my screen now?
perfect. So yeah, we can see the slides and hear you clearly. Go ahead with your presentation.
Yeah, hi. Hello, everyone. So I am Shah Hassan, and I'm going to present the paper performance evaluation of boosted to stream TCRnet. And this is co-authored by MD Jibanul Haq Jiban and Dr. Abhijit Mahalanobis. And we are from University of Central Florida Center for Research in Computer Vision. Let me talk a little bit about our motivation. So the task here is to detect vehicular target in the midwave infrared imagery. The target could be between 2,500 to 3,500 meters away from the camera, like you can see an example of the pickup vehicle here. Yeah, so the task is challenging for various reasons, like very low signal to noise ratio. The target occupies very small number of pixels in the image. The background is full of clutter. There can be many weather related variations and also different kind of obstructions as well. So in one of our papers, we proposed this two-stream TCRnet, which uses a fixed predetermined filters in the first layer of the network, which is analytically derived. These filters are eigenvectors that discriminate between target and clutter. So keeping that first layer fixed, the rest of the network is trained using gradient descent to also maximize the same the same metric TCRnet. So as shown in this figure, there are like 70 target and 30 clutter filters in the first layer. And within each stream, the output of the first layer is processed by two more convolution layers. Then the output is concatenated and a final convolution layer is applied to produce the combined output. Targets are then detected by finding the local maxima in the final output activation map, which is produced by this network. So this is different from the original TCRnet, which is only single stream, which does not process target and clutter stream in two different channels. Let's also briefly review the filters in the first layer, which is target to clutter metric, in short TCR metric, which is the key to this TCRnet or TCRnet2 approaches. This is used not only as the cost function, but also by for analytically driving the fixed first layer filters. So here this TCR is the TCR metric, R1 is the correlation metric, and R2 is the R1 is for target and R2 is for clutter. Both of them are correlation metrics. Qi is the eigenvectors or the basis vectors. So the intention is to maximize the product of the target energy and minimize the sum of the clutter energy. And it turns out that the dominant eigenvectors corresponding to largest eigenvalues best represent target, while those corresponding to smallest eigenvalues principally represent clutter. And here you can see the visualization of domain eigenvectors for targets and for clutters. This is the TCR cost function, which is used to train the network, except as I mentioned, the first layer, filters in that layer are analytically derived and fixed. So yi is the individual clutter response, xi is the individual target response, kind of a reciprocal of the previous TCRnet metric, which we discussed. It is arithmetic mean of the energy of the target samples divided by geometric mean of the energy of the target. So the clutter is there and the target is at the bottom. So minimizing this will actually make the numerator small, which will make all the clutter terms small, and that will make the denominator large. That will ensure the target terms are large. This slide shows the concept of boosting the output of the TCR-net2. The first network is used as a primary network to nominate the region of interest or ROI that may contain potential targets. And the second TCR-net2 network with the same architecture is then used to detect the target with the intention to further boost the score of the true target among the potential targets detected by the first primary network. So the final detection score is the sum of the confidence score produced by these two networks. The main difference between primary and secondary detector is that the network is same, but the primary detector is trained on target chips and randomly selected clutter chips, whereas secondary network is trained on the same set of target chips, but the clutter chips are only the false positives produced by the primary network. So the data set we have used is from DSIAC, which I think Defense System Information Analysis Center. It's a large collection of mid-wave infrared imagery. It has 10 different kinds of vehicular target collected both during day and nighttime. The range of the data is between 1 to 5 kilometer, both inclusive. And the size of the image is 512 cross 640. So you can see example on the left, the pickup vehicle is 1 kilometer away from the camera at nighttime. In the middle, the pickup vehicle is 2.5 kilometer during the daytime. And here, the pickup vehicle is 3.5 kilometers during the daytime. And it looks like that the nighttime scenario is less challenging than the daytime. And that will also show in our result. We have split the train and test data as follows. We trained the network on images of ranges 1, 1.5, and 2 kilometer ranges, where the chip sizes are 40 cross 80 size. And we trained on around 10,000 target chips and 10,000 clutter chips, and the images are scaled for 2.5 kilometer range. Here, these chips are part of our training data. The top one is the target chip and the bottom one is the clutter chip. And so on the test side, the test data consists of full images of ranges 2.5, 3, and 3.5 kilometers. There are around 10,000 images on which we tested the network. And we tested in both kind of scenarios, that is on scaled images as well as on unscaled images. And we are going to show the results for both of them shortly. So here you can see an example of the full frame test images. So the qualitative result shows that the ground truth is there on the red bounding box. The yellow ones are the potential targets. And we can see that the true positive target has the highest detection score of 5.54, which is higher than all others detection. So let's talk a little bit about our detection strategy. So the network produces the output intensity values, and the detection is performed by searching the local maxima on that. we would want to maximize the response of the output at the target location in order to produce a strong peak at the output, which provides both detection and localization. To make the scores comparable, the potential detection scores are further standardized by extreme value distribution. And in this diagram, you can see the output activation map for the given test image. Let's talk about results in terms of ROC curve. On the left, we have the detection rate with respect to false alarm per square degree for both day and nighttime scenarios. And we can see that two stream one, or the yellow one, is better than the original TCR net, which is the red one, and the green one, which is boosted TCR net, is even better than the two stream TCR net. We can see that two stream and boosted techniques have helped even more with the challenging scenarios. For example, the daytime images, as you can see on the right side, and here, two stream and boosted two stream are shown in yellow and the green curves, respectively. For these ROC curves, we can see that at a detection rate of 0.82, the two stream TCR net and boosted version, both of them achieves they achieve a FAR value of 0.25 and 0.15 respectively, which are around 8 to 13 times lower than the original TCR net. And during the daytime only scenarios, these values are about 5 to 10 times lower than the original TCR net. Here are the results for different scenarios, like only daytime, nighttime, and both times. The results show that, as I was showing in the one of the sample test images, nighttime is less challenging scenario for an infrared camera. And for example, at FAR of 2.0, TCR net, the boosted TCR net 2 is able to achieve the detection rate of 0.84 for the daytime and 1 for the nighttime. FAR 1.0 also gives detection probability of 0.8, around 0.8 for the daytime and 1 for the nighttime. So now the results shown in the previous slides were on the scaled test images when the radius is fixed of 20 pixels. Here we can see that the ROC curves for the TCR net and the boosted TCR net, they do not change substantially when the test images are not resized using the range information. And in order to test that, we define the detection window with this formula. Instead of keeping it fixed, we define a variable detection window. Hence, we can see that the dotted line.
2 minutes more. Sorry for interrupting you, but 2 minutes more if you wanted to complete.
Okay. Yeah. So the dotted lines in the ROC curve is not substantially bad. Last but not the least, we also introduced this simple CNN classifier as well for the detection of the vehicular target. So in order to classify the kind of vehicle in the test images, we also propose this MWIR target classifier that consists of an input layer followed by 5 convolution layers, followed by 1 fully connected layer and a classification layer. We train the MWIR target classifier on 32 cross 64 chips with vehicular target at the center. The chips are extracted from the images of ranges 1, 1.5, and 2 kilometer ranges. And we test this classifier on the detections from boosted TCRnet 2 in order to complete that pipeline. First detect and then classify the vehicular target. MWIR target classifier achieves about 65 to 66% accuracy on the NVESD dataset. So with this, we'll conclude our discussion with we showed that two-stream TCRnet and boosted TCRnet performed substantially better than the original TCRnet. Boosting has even helped even further. And we also showed that TCRnet 2 is robust to range variations, and we don't necessarily have to manually resize or scale the test images using the range information. We also introduced a simple CNN classifier that can achieve the classification accuracy of 65.72 on the NVESD dataset. And these are some of the references, some of the key references, and thank you all.
Thank you.
Thank you for the presentation and all the best for the rest of work. We don't have questions on the chat, so it's over to you, Professor, if you wanted to ask or discuss any point.
Yeah, I wanted to know in this scenario, which one is more significant? Is it the range information, or if you consider the number of vehicles? For instance, I thought.
So none of them are significant. We also showed that even if we don't use the range information, we are able to produce a.
Okay.
Can you hear me?
Yes, I can hear you.
Don't use the range. So none of them is significant. Like, it doesn't matter if we have more than one vehicle, we are able to have same detection probability with respect to FAR. And the other thing you said, range information, we showed that in one of the slides. Even if we don't manually resize the image, we are able to achieve substantially good detection probability.
Good. I think that's all. It's a good work.
Yes,
all right.
Thank you, Professor, and thank you for the presentation as well. All the best. So now we are heading to the last part again of the session. So thank you again. In brief, thank you, Professor, for your time and efforts. In conclusion, we came to the end, and we hope that you have the capacity to join us tomorrow. In the next session. We can also take a picture for a memory of this day, even it's virtual. So if possible, could you please just turn on your cameras, and I will take a screenshot for our recording, and for sure it will be showed here. Yeah. So yeah, thank you again, and all the best.
All right. Thank you.
3, 2, 1. Okay, it's done. All the best again, and we hope to see you tomorrow.
Thank you.
Thank you. Bye-bye.
Okay, thank you.
Stay safe. Bye-bye.